Efficiency analysis of waste heat recovery systems using the case study of a cement plant. Abstract A. This paper analyzes the efficiency of waste heat recovery system, WHRS, at a cement manufacturing plant of a cement major which is a pioneer in sustainable cement manufacturing in India. The paper also identifies factors possibly affecting the efficiency while using data to evaluate models, including a novel mathematical model for the effect of impurity concentration on efficiency. Analyses of a few alternatives have also been provided. Therefore, this paper provides a detailed efficiency analysis of smart energy systems. Introduction. Heat loss or heat dissipation is a major problem faced by most industrial sectors. It leads to losses in efficiency of various industrial processes and results in negative effects such as environmental degradation and monetary loss. Minimizing the negative impacts of this consequence can take two forms, which are heat loss reduction and waste heat utilization. There are various ways to implement these strategies in cement manufacturing processes, and this paper will focus on the WHRS or the waste heat reduction system in the plant, which is a pioneer in sustainability and smart energy systems in cement manufacturing processes in India. Utilization of heat loss by the WHRS or the waste heat recovery system. Minimization of heat loss reduction in particle size. Reduction of particle size in hammer crushers, impact crushers, secondary crushers, VRM hoppers, and raw mill hoppers along with nodulization in rotary kilns, all increase the rate of heat transfer, thereby causing reduction in mobility of heated masses and reducing time in which heat is lost. Assuming a constant rate of heat loss is therefore reduced. Introduction. The WHRS at the plant uses a thermoelectric approach in order to recover and utilize lost heat energy. Boilers installed at strategic points of greater heat losses and a single turbine compose the main machinery utilized. As seen from Figure 1, boilers have been installed at the suspended preheater, SP, and at the air-quenched cooler, or the AQC. These are two areas where heat liberation is the maximum due to greater drops in temperature. Coolers cause material temperature to drop from around 1400 degrees C to around 1300 degrees C. Therefore, the SP2 and AQC2 both have boilers nearby where heated air is passed into. The steam condenses back into water and is recycled. It is passed into the water cooler after the power plant with the generator and turbine and is then lead through pipes and distributed to the various boilers using a water pump to pump the water. Data gathering K1 preheater. Efficiency. The efficiency of different systems will be evaluated differently. The power should be directly proportional to volume, as it is directly proportional to mass. The turbine rated at 9 MW generates 7.20 MW of electricity or energy, which leads to 0.80. This shows that the approximation made earlier is a suitable one and may be used in order to evaluate individual efficiencies of separate boilers. Probable factors affecting the efficiencies of the four individual boilers. Inlet smoke dust density. The additional 0.06 decrease in efficiency from 0.83 to 0.77 may be due to a factor not accounted for, such as differing gas densities or specific heat capacities at different temperatures. However, this approximation seems to be adequately accurate up to one significant figure when efficiency of the AQC1 boiler is taken as 0.95. Therefore, efficiency of the AQC1 boiler will now be considered to be 0.95. B. Aerodynamic Convection Kinetic Energy Recovery System, ACERS. Heated gases may be lead to a container containing a turbine through an air inlet. Convection will lead to the formation of electricity, as the kinetic energy of the heated gases will be converted to the kinetic energy of the turbine. There may be one air outlet to let out cooled gases and allow more heated gases to enter. The air outlet may have an ESP or electrostatic precipitator installed. This may lead to reduction in steam transmission losses, reduction in water usage and elimination of the need or the requirement for the boilers. However, it may lead to greater fluid or gas leakage, unequal electric outputs due to multi-directional or. However, practically, 3 equals 0.90. Even up to a single significant figure, there is a deviation of 0.1. Without the application of the quadratic model relating efficiency with concentration of impurities, 3 equals 0.83. Although the deviation may be smaller, the increase in 0.83 to 0.90 is difficult to explain given that specific heat capacities and the density of air would be expected or estimated to be lowered by heat losses on fluid mixing and air, gas, or fluid transmission, which would yield a lower value of efficiency. Therefore, it can be concluded that the quadratic model may provide an explanation for the aforementioned increase in efficiency. Deviations may be due to heat losses not considered or fluctuations in values such as specific heat capacity and densities of air. Evaluation of alternatives. A direct heat utilization. Heated gases may be redirected to points of the cement manufacturing processes where heat is required, for example, as a replacement of or supplement to the hot air generator or the HAG feeding heated air into the VRM or vertical roller mill. This maximizes efficiency since efficiency reduction in energy or electricity generation machinery and in boilers reduces. The number of heat exchanges is also reduced, thereby reducing heat losses due to imperfect thermal system isolations. Energy requirements for water cooling and pumping are also reduced. Water requirements are reduced for the boilers. Boilers may not be required and therefore, capital costs may be reduced. However, according to the second law of thermodynamics, there will be energy losses and this may not be an infinitely sustaining system. Reduction in velocity of hot or heated gases during transportation may require pumping and leakages may cause the requirement of supplementary HAGs. Electricity generation using magnetohydrodynamic, MHD, generators. As seen from the diagram, MHD generators collect heated gases and creates electricity, working similarly to a fluid dynamo utilizing plasma. Although this technology may be extremely beneficial in terms of reducing water and boiler usage, it generally has low efficiency and is expensive. Heated gases also must be at a very high temperature. Utilizing thermionic generators to convert heat energy of heated gases to electrical energy. The riser tube of boilers may be installed with the cathode and anode of a thermionic generator. Thermionic generators may also be used without boilers, thereby, once again eliminating the needs of water and boiler usage. However, high costs for materials like the cathode or the emitter of the thermionic generator may be a disincentive to install such technology. Although many of these alternative technologies may reduce water and boiler usage, capital costs may be high. Given the already high efficiency of cement manufacturing at the plant, a cost-benefit analysis would be preferred before switching to alternative technologies that may lead to restructuring of the PFD and the infrastructure of the plant. However, from the view of sustainability, the first option may lead to multiple cycles through the ESP, thereby increasing pollutant retention and decreasing the pollutant concentration in emissions from the plant. Conclusion. The cement manufacturing plant is truly a pioneer in terms of sustainable design and its WHRS. Although alternative technologies for the WHRS may be proposed, high efficiency values in its present WHRS may act as a disincentive to switch technologies without great efficiency gains or sustainability gains. Other cement manufacturing plants in India and other industrial plants should consider similar technologies in order to reduce emissions and take a collective step towards carbon neutrality along with waste heat recovery and heat loss utilization.